So we're talking about activation energy, and we remember way back when we looked at potential energy curves for reaction. So let's say we have some reactants going to products, and we were to plot that in terms of potential energy, and we would have, let's say, this reactant and changing to, let's say, this product, and this would be a potential energy curve. And this would be a plot of energy. And here's my energy here. And this is some kind of time coordinate. And essentially we learned that the difference of where we started our energy level and where we finished was that state function called enthalpy. More importantly, we looked at this value here, this little, from the energy that we started to the top of the hill as our activation energy. We're going to call activation energy E of A. Okay, it's a really important term, and it has its implications with the rate law. Now, this little value here, this hump, is essentially the amount of energy that prevents a reaction. So we have to overcome that for reactions, and all reactions have that, okay, little area that prevents the reactions to go. And that's an important barrier. So that's basically a reaction barrier that prevents all reactions from just going. So this is an exothermic reaction. As we see the delta H, or the change in energy, dropping, our value would be negative as energy is lost to the environment. But this is a reaction barrier, and every reaction has one. But the size of the reaction barrier, okay, determines how fast a reaction goes. So it's very important when we talk about E of A that you're imagining this little drawing here. Okay, now very simplified as I showed you, as reactants go to products. It isn't always this simplified. As we looked in rate law, we often have mechanisms, which is a series of steps as reactants become products. Very rarely is it one single elementary step. So this is the overall energy needed to get to this top of the hill where the reaction would go. All right, so again, very important size, this value from here to here that is related to the value of your rate law constant. Okay, now as you remember, rate law is equal to the value of your rate law constant times, let's say, the concentration of a reactant. Let's pretend it's a first order. And as you can see, your rate is in molarity per second of either the decrease of A or the increase of the product. But it's directly related to the value of K. If the rate law constant increases, clearly your rate is going to increase, and vice versa. So where does this activation have its implications with K? Well, it really starts with the Boltzmann distributions. Okay, so if I was to erase this, okay, and draw a Boltzmann distribution graph, okay, as we've done so many times, remember a Boltzmann distribution is the distribution of all the kinetic energies. So if we call this, let's say, speed of molecules, which is tied to their motion energy, and this y-axis is the number of molecules, you can see that at a certain temperature, okay, we have a range of speeds for molecules. Okay, and we can call this hump, let's say, let's make this at 30 degrees Celsius. Now, as it gets colder, okay, this distribution of temperatures actually gets higher as it gets impinged upon the slowest speed. Now, the slowest speed is related to what? The coldest possible temperature, 0 Kelvin. So temperature is directly related with these motions. As temperature increases, what do we know? That the molecular speed proportionately, I should say, increases. All right, now, what do we know? Well, at a certain temperature, okay, there is a threshold for that activation energy, E of A. So let me just draw it. So this would be a dotted line that's supposedly straight, and again, I'm not too, my drawing here isn't very straight, but this would be my E of A. Okay, and what does this mean? This means that at this activation energy, I have this many amount of molecules have the what? They have the energy to overcome that activation barrier that I just erased, okay? So this fraction that I just drew by my quasi-straight line here shows me that this is the fraction of the molecules that have the energy to overcome, let's say, the repulsive forces. Remember, this is about atoms colliding. And when atoms collide with enough kinetic energy, okay, bonds can be broken and reformed. It's all about collisions. Now, why would we need energy to do that? Well, first of all what? Molecules have a cloud of electrons around them. So there's going to be repulsive forces that we have to overcome. And there's also what? Attractive forces with the other atoms. So overcoming attractive forces and these repulsive forces is why we need enough activation. Of course, they have to hit with the proper orientation as well. But we're after today about this fraction. So this threshold that represents the amount of molecules that can overcome this reaction barrier and now react, okay, is delineated by this E of A. Now, if the activation energy was to drop, okay, it would go that way. If the activation energy was to drop, we would have to draw our line here to go in this direction. So if our activation energy drops, we can see that this line would get smaller. So my activation drops. Now, if my activation energy drops, you have a lower amount of energy to what? Overcome, or that reaction barrier that's preventing the reaction from going is now smaller. So here's my reaction barrier, and if I was to lower the activation energy, it's now a smaller value. A smaller value will mean that the reaction will go faster. Well, why? Well, if you think with me for a second, if I make the activation energy smaller, and now I move it back, let's say, to this line, okay? Now, moving it lower means it requires what? Less energy. Remember, speed is a value of kinetic energy. So if the kinetic energy is what? Less as I go this way, you can now see that I've got a greater amount of molecules who have enough kinetic energy to overcome these repulsive forces or these attractive forces. Okay, so you can clearly see that by decreasing the E of A, I have more molecules who have a greater fraction of energy to react. Therefore, there must be an increase in K. So as the activation energy drops, this gets smaller. Okay, more molecules have the energy to overcome this barrier. So there must be an inverse relationship between lowering the activation energy and the value of K. So the K, and then this is not KQ, this is the rate law constant, we said increases, and it's going to make the rate increase based on our rate law. Okay, and so when does K increase? When activation energy drops. Now, we can drop the activation energy by adding a catalyst. Okay, that's important. So a catalyst, okay, as we can see, can decrease the activation energy. It can lower that. And you guys learn that it makes an alternative pathway, and that could make that dotted line. Okay, and we'll talk about that in a second, but let's go off into what temperature by itself can do first. So we know we can lower the EA by adding a catalyst, and we'll talk about that in a bit. But let's talk about what temperature itself can do. So we know we can lower the EA, and we do so by adding a catalyst, but we also can change this fraction by changing the temperature. See, we know that this rate law constant is temperature sensitive, just like KQ is, but for different reasons. Now, why? Well, let's go back here and let's clean up my drawing and make some room here for, I guess, a newer one. So we have this drawing. Let's go back to our original fraction, and let me get rid of this, and let me just kind of redraw this little hump. And we can see that the E of A is right here, and only a small fraction can overcome this reaction barrier. Now, what I'm going to do now is increase the temperature. So let's go with a magenta. If I increase the temperature, this distribution of speeds kind of flattens out. Okay. Now you notice by increasing the temperature, what did I just do? The EA, or the activation energy, stayed constant, but now I have more what? I have a greater fraction of molecules that can overcome that activation energy. So by increasing the temperature, I'm giving a large number of molecules the energy to what? Overcome the activation energy. So increasing the temperature also equates to a higher K, because now more molecules have enough energy to overcome this reaction barrier. So you need to be aware that the value for K is dependent upon the inverse relationship of activation energy and the direct proportion of temperature. And we have a reaction, or we have an equation that I will not derive for you, okay? It's not part of the AP chemistry curriculum anymore, but one that I do want to look at. Let's just move up here for a second. And basically, the equation goes the natural log of K, and it kills me not to derive this, okay, is equal to the negative EA over R, gas law constant, okay, times the 1 over T times the natural log of A. So what this is all the concentrations of A, assuming they have all the kinetic energy, times this fraction, or this value that's going to minimize that. So if we assume that every single concentration of A has the energy to overcome this barrier, okay, then we times it by this component that, if you notice, it's a negative. It's going to decrease that value. Now notice something, party people. Look at the E of A. It's directly proportionate to the K. Look at that. You increase the EA, okay, as we just did here in our distribution, okay, you can see that it's going to make it a larger negative value. So if you increase your EA, it's going to make the fraction smaller. Therefore, it makes it a greater negative, okay, which will lower the number of available atoms that have the energy to overcome this barrier. Look at T. If I was to change temperature, notice that's an inverse relationship there, as we talked about. So you need to understand that K is equal to temperature, or I should say proportionate to temperature, and K is inversely related, okay, with E of A, right? So as activation energy increases and you move this line forward, there is less lower rate constant. Okay, so you can see that if I increase the temperature, as I talked about, and this line extends outward, and this being the EA area, we have more what molecules. So if I increase the temperature, I make this a bigger number, this overall expression becomes less negative. Therefore, it increases my K, which means there are more molecules who have the barrier. All right. If I decrease my EA, move it this way, what happens is what? The value of EA, okay, gets smaller, and this becomes a smaller negative, which means my K increases. The positive value here increases. Why? As I move A this way, there are more molecules that have a greater amount. All right, last little piece here. How does a catalyst affect this reaction barrier? You learned last year in my potential energy curve, a catalyst changed the pathway. Well, that's a lame-o way to explain it. So if I have a reaction that's uncatalyzed, I'm going to go from this bunch of reactants to these bunch of reactants. If it's uncatalyzed, okay, it needs this amount of activation energy. If I catalyze it, okay, what I do is I start a whole series of reactions that will, in fact, have a lower activation collectively. Let me explain. If I don't have a catalyst, I am not going to have a mechanism that causes two steps. So in the catalyzed reaction, there's two steps. In the uncatalyzed reaction that I'm showing you here, there's just one step. So in the one-step process, the activation energy is huge. If I catalyze a reaction, okay, I'm going to have two steps. And these two steps changes the entire pathway in the reaction. Notice the two little humps? This is the activation energy of the first reaction, and this is the activation energy of the second. So by adding a catalyst, it creates a new mechanism appearing that collectively, okay, creates a sum of these activation energies, okay, EA1 and EA2, this is the first one, second one, that's overall what? Lower than the original. That's really vital. So last year, when you learned about potential energy diagrams, you learned that what? You lower that hump. Well, the reason is because a catalyst is going to create a mechanism. And that mechanism, if it's a true catalyst, will create a series of reactions that have an overall activation or what? A limit to what you need to start the reaction to be smaller. So that reaction barrier has been lowered by the series of reactions when you add their individual what? Activation energies. Inhibitor would start a whole series of reactions where all the activation energies now are bigger. Okay? So that's important. You understand that. All right? So that is the major understanding for when you use something called the Arrhenius equation. Although we're not going to use it, you need to understand how activation and temperature affects the value of K. Hope that helped.